Threads. Threads are great. Threads are the non-toxic glue of the engineer's toolbox. So accessible that even your first year engineering student is able to use them. So old that your mom uses them to press olives and grapes into oil and wine. And so commonplace in your daily life that you'd hardly notice its existence. Yet without it, you'd break more light bulbs.
Just screw it nice and tight and it'll turn on.
More tires would fall off, and that IKEA furniture you're sitting on would probably collapse. Actually, it'd probably already do that on its own. What's food doing here? Ooh, that should not be there. Threads provide a simple yet elegant solution to the challenge of converting rotational motion into linear movement. They also can be used to prevent linear movement, utilizing the friction between the two threads to act as a fastener. Traditionally, we have been able to make threads with techniques such as cutting, casting, milling, or tapping. However, today, we will explore the process of designing and printing threads for use in a high-powered rocket. But first, a word from today's sponsor, PCBWay. PCBWay is your one-stop shop for PCB fabrication, 3D printing, and CNC services. They make it easy for you to get started on your next project by offering high-quality prototyping and manufacturing services with fast turnaround times. I can attest to this because I use their PCB fabrication services to make these screw switches for powering on my rockets. As someone who's always been limited to a breadboard, PCBWay's customer support and guidance made it an easy and approachable task to make my PCB designs a reality. Thank you again to PCBWay for sponsoring today's video. So, how do we make threads? Well, you could just go into SolidWorks, open up Hole Wizard, and select from a range of different thread options. However, this is a bit limiting as the range of thread sizes are far too fine for our applications. The other alternative is to make our own threads from scratch using the helix and sweep tools, where we can then control the pitch and cross-section of our threads. This gives us better control over the angles in our threads, reducing the severity of overhangs and improving the overall printability, as it's always good to avoid supports. For this design, we will incorporate threads into components such as the switch band, lower airframe, and motor tube adapter so that the rocket can be easily assembled and ideally have parts that can be used interchangeably between designs. We then outline the design of the rocket using a simulation software such as OpenRocket, so that we can design while keeping in mind things such as stability and center of gravity. It also provides configurations for different motors and plots out the expected path of our launch. For this, we'll be using a dual deployment system consisting of a drogue parachute to reduce the shock from the deployment of our main chute. Now, let's go and build this rocket. about 2,200 feet. And it's going in 5, 4, 3, 2, 1. 2,200 feet?
Alright. Yeah, I think it made it.
Yeah. Yeah, it seems it made it a lot more than it should.
It looks like it's something coming down pretty quick. Yeah.
Uh-oh.
As ballistic.
I saw it turn over and come straight down.
Oh. Is that recoverable?
I don't think so. As you can see, I was able to get my rocket to go up, but getting it back down safely, well, let's just say that there's a lot more work to be done there. So off we go to search for the remains of my rocket. So it says go that way. Keep going like this way?
It's trying to take us back to the launch site.
Oh.
Is that a lost log?
I did see it go down like that way. Nope, not it. Ooh, that is really bad. It's around here. It's like
We should have worn brighter colors.
yeah.
This thing was still sending us on a wild goose chase. At one point it started rising by like several feet per second.
Buried in there.
Oh my god, it's like in there.
Oh god.
It's stuck in the dirt. Oh wow. Okay. So there's, what is this?
Oh no.
Do you think I can get the run cam from here?
I think you'll be able to get everything out. It's just a matter of like slowly chipping away at it.
Yeah, completely crumpled.
Okay, yeah. Well,
Let's
take
take
it.
it
Yeah, there's too much plastic as it is. Okay, it's right here.
There we go. Solder it back on. Easy.
Yeah, totally would work.
It
Oh wow, that 9-volt is kind of crushed. And yeah, this is kind of, oh no, that means the Stratolog is probably dead. The screw switch seems in pretty good shape though. I might keep this. Oh, that's like, that is
Oh no.
half a board.
There's the other half.
Board split.
Ah, I see. Nice. All right. Oh, nice.
All right.
Nice. It's
Any kicks?
it's all in one piece.
All right.
There you go.
Hooray!
I've seen bent motor cases before, so that's a good
Flyable
sign.
condition.
Oh, yeah, there's a rip there. But it might just be, oh no, the parachute's kind of ripped as well.
No, it's fine.
It's kind of melty.
This is small. I've flown with holes bigger than that.
All right. So it's still flyable, I guess.
Yep.
Um,
These are garbage. We should sort them out.
yeah. All right. I think that's everything. Hopefully better luck next time.
Thanks for watching Peter's unboxing.
With some investigation, the parachutes failed to deploy due to an inadequate amount of ejection charge, which I would have found out earlier if I had ground tested it. With all this, I was super fortunate that only my rocket was damaged in this flight. After all, these things can be rebuilt. Next time, I'll be sure to check off all my boxes before launching to avoid another expensive lesson like this. Thanks again for watching, and thank you to everyone who helped me create this video. See you again next time.